Hello and welcome students to the second to last lecture of the spring semester Chem 202. I hope that you are all surviving as well as you can, thriving as well as you can. I have already given the announcements that I feel like I need to in the previous lecture pertaining to like homework expectations for the finals. So let's just jump into it. So we are going to be introducing some new material here with the topic of standard reduction potentials. So what a standard reduction potential is a measure of the energy of the electrochemical cells that we topically introduced in the last lecture. So let's get into how we calculate energy of these types of electrochemical systems. The type of cell that we are going to be studying is known as a galvanic cell. There are a couple of other cells, cell being like structure or like physical like build or makeup, the construction of like what your reaction vessel kind of looks like, how it's connected. The type we're going to be talking about is a galvanic cell. The definition can be seen here. This is an electrochemical cell in which a spontaneous redox reaction is going to be doing some type of electrical work. So the key words here are electrochemical, which we learned what electrochemistry was in the last lecture. So it is some type of chemical reaction where electrons are transferred. And in being transferred, we're going to be doing some type of electrical work. In other words, there is going to be some measure of energy. So the various forms of energy that we've introduced before are like thermal energy, mechanical energy, physical energy, kinetic energy. So here we're going to be talking about electrical energy. So this is the work that is done as electrons move from place to place. The last key word that is really important in this definition is spontaneous. So here we are going to be looking at chemical reactions where our Gibbs free energy is less than 0. These are reactions that move forward after the activation energy is put in and just continue on their own. So these are going to be electrical cells that are going to then be generating energy after the reaction gets started. Again, if we think of something like a battery, there is a chemical reaction occurring inside of a battery that is expending chemical energy. And if we put that battery in a device like a cell phone, the cell phone then is going to be using that electrical energy, to accomplish whatever it wants to accomplish, whether it be you're, making a phone call or streaming the internet, whatever the situation is. But it's this energy that we are going to be studying. This energy is known as the cell potential. It is the potential energy that is held within the battery or within the cell that has the chance then to, over the course of the chemical experiment, be expended or released into the environment for something else to pick up and use. In terms of calculation, our cell potential is the experimental difference between the electrical potential between our anode and our cathode. This is, in other words, between the negative and positive end of our battery. So on the right, we have a depiction of some type of galvanic cell. So like the physical build we can see here on the right. Here are some important components of a classic galvanic cell. The construction obviously is not, if you've ever seen like a lithium-ion battery or a Duracell battery, this doesn't look like those. But this is the kind of like precursor to the construction of like a more modern battery, where we have on the left-hand side what is labeled as the anode, and we're going to be defining anode and cathode here in a second. But the important thing for now to recognize is we have some solid material as well as that material being dipped in a solution of its own ionic composition. On the right-hand side, we have a different material, in this case it's copper, which is dipped in a copper 2+ solution. So here we have like free-flowing ions where we have learned that electricity can be conducted through ionic solutions. So we have ions that are present, and we have two solid materials that are clipped together. And the electric potential difference between these two sides, the left and the right, is the measure up on the top. So we would be able to predict based on this experimental setup that the electrons that we can see are being transferred from the cadmium to the copper, the difference between these two, or like the number of electrons being transferred, is going to be the equivalent of 0.74 volts. So let's get into what the anode and the cathode technically mean. And so in doing so, we can get a better idea of like what this construction is, like what is a galvanic cell based on these two different electrodes. All right, so an electrode is a component of an electrochemical cell, like the galvanic cell we just looked at, where there is some type of oxidation and reduction occurring. So here's where we can see the explicit tie-in to redox chemistry. If there is some type of electron that is being, or a number of electrons that are being transferred from one side of a battery to the other, well, that means there has to be some type of redox reaction occurring from one side to the other. And so we label the anode, where there is some oxidation occurring. So I've bolded these letters now. I've also kind of outlined them because the way that we kind of like conventionally teach people to remember that the anode is where oxidation occurs is because there's right here we can see a picture of a blue ox. The cathode is where reduction occurs, and on the right we can see that there is a red cat. So an ox, red cat. It's just like a cute little way to remember that the anode is where oxidation is occurring and the cathode is where reduction is occurring. And so if we tie the previous illustration into this example, or these definitions, the examples we can see below, where the anode was in the previous diagram labeled where like the cadmium was and the cathode is where the copper was. Since the anode is where oxidation occurs, that means that the cadmium was being oxidized. The solid cadmium was turning into more or producing more of that cadmium 2+ in solution and also generating 2 electrons in the process. So for every 1 solid cadmium that dissolves in solution, we get 2 electrons. And these 2 electrons are going to flow over to the cathode side where copper in solution is combining with the electrons and then is being reduced into copper solid. And so we now have an illustration for what this type of reaction not only looks like, but a new form of the construction where instead of just mixing 2 solutions together and it's like, oh cool, this solid's turning into another solid, now we actually have a clever construction where we are purposefully forcing the electrons, just to go backwards, we're purposefully forcing the electrons as the oxidation occurs on the left-hand side to flow through this wire into the cathode on the right-hand side. Now, instead of a voltmeter being here, we could have some type of device present instead. So we can have not only electrons flowing from the anode to the cathode, but also some of the electrons kind of being dispensed into this device instead. So like the battery is actually going to be useful to power some type of like external source. So that is the kind of like gist behind the construction of this galvanic cell and why we have it looks so strange, but it's actually very useful because we have a way to actually extract the electrons that are being transferred throughout this chemical reaction. All right, so again, an ox, red cat. That's how we can remember which side, which electrode goes along with which half of the redox reaction. The anode is where oxidation occurs, and the cathode is where reduction occurs. All right, so now we have, let's learn a naming convention or like a labeling convention for this type of galvanic cell known as a cell diagram. So the example that is directly below this notation is what like the formatting for a cell diagram is. So we list the anode on the left-hand side, the far left with a single vertical line between it and the anode solution form. There is a double line then between the anode and the cathode, where the cathode solution is listed next, single line, and then on the far right, we have the solid form of the cathode that is present. So this is a really nice shorthand way to illustrate or kind of infer what your illustration of the galvanic cell below would be. So like if you were to have a cell diagram presented in front of you, you could draw the actual galvanic cell kind of like mirroring this illustration type below. Or if you were given a galvanic cell, as is given to us, we can write out what the cell diagram is. So let's do that now. So our anode portion of the galvanic cell is the cadmium side. So we would list out cadmium solid with a single line between it and the cadmium 2+ aqueous, double line between that and the copper 2+ aqueous, single line between that and the copper in its solid form. So here is the total cell diagram then that corresponds to the galvanic cell that we have illustrated on the right. All right, so that's the purpose of the cell diagram, is just to give you a nice shorthand representation of your galvanic cell without having to take up so much space in drawing your galvanic cell. But what if we wanted to go the other way? What if you were given a cell diagram and, as you are here, being asked to draw the galvanic cell that corresponds to that cell diagram? Now again, galvanic cells in terms of like physical construction can take up a number of different forms, but we are going to learn to draw the like kind of classic image of the galvanic cell. We're also going to label the cathode, the anode, and the direction of the electron flow. All right, so as we just learned, the left-hand side is the anode piece of the cell diagram, which is where oxidation occurs, right, anox. The right-hand side of your cell diagram is the cathode, where reduction occurs, again, red cat. How you can remember that anode is on the left of your cell diagram and cathode's on the right is because the two are simply listed in alphabetical order. A in anode comes before C in cathode, and so your anode is always going to be listed on the left-hand side, and this is always going to be the side that represents the oxidation step. All right, so let's draw our galvanic cell. Let's have some fun drawing a picture. If you don't think that you're that good at drawing pictures, totally fine. We can draw this in a very simplistic form. So first and foremost, I am going to draw the kind of like piece that I haven't addressed yet that held our two, let's do it this way, beakers together. This is known as our salt bridge. All right, now we'll get into the details of what the salt bridge is in a split second. So here are my beakers that the salt bridge is in, connecting our two solutions, where on the left-hand side, we're going to draw our anodes. So we have aluminum 3+ floating around in solution. On the right-hand side, we have the copper 2+, that's floating around in solution. In addition, we have to draw the actual physical electrodes themselves that we are going to connect, where the transfer of electricity is going to occur. Solid aluminum, Al solid, is going to be on the left, and we have our solid copper that is on the right. All right, we're going to connect these two electrodes via a wire, and since the anode, again, oh, I lost my pen, there I am. Since the anode is on the left, anode, this is where, again, oxidation occurs, where oxidation is the process of electrons being lost. So we are going to be losing some aluminum solid. As the aluminum solid is going to slowly dissolve into solution, we're going to get a flow of electrons from this aluminum solid up into the wire, moving towards the copper solid, which is down over here. This copper solid then is going to be pulling the copper 2+ from solution onto itself, combining with the electrons. All right, so now let's talk about what the salt bridge does. Here we have our kind of complete, simple illustration of our galvanic cell. Oh, and I should probably also complete cathode is on the right. This is where reduction occurs, since I need to label the cathode and the anode. We also have the direction of our electrons, our electron flow being labeled here from the left to the right. If we draw our anode on the left, we are always going to have the electrons then flowing from left to right. All right, enough. What is the salt bridge? The salt bridge is a bridge between the two aqueous solutions that, let's draw it down here, assists in keeping charge balance. because as we have electrons flowing from the left-hand solution to the right-hand solution, we, if there's no charge balance, if there's no salt bridge present, we're just going to get this buildup of negative charge on the cathode side, and that's no good. So what the salt bridge is useful for is it actually allows some of our positive ions from the left-hand side to kind of sneak up and move into solution as well. So for every like 3 electrons that move from left to right, that move from the anode to the cathode, we're also going to have a single Al3+ move across the salt bridge down into the solution on the right. And that way we are keeping charge balance. Now, if you're wondering whether or not the Al3+ has the chance to like then be reduced onto the copper solid, the answer there is no. The Al3+ is more easily oxidized in this reaction, and so it will remain in solution, and it will then continue to be the copper 2+ that is lost from the solution on the right and moves up into the copper solid as the copper is reduced. All right, so that's the purpose of the salt bridge. That's why it's been in the illustrations, and that's why it's important to also include it in any illustration of a galvanic cell that you have. So here we have the electrodes that are present, we have the solutions that are labeled, and we have our salt bridge, which is helping to keep charge balance. So now that we have the illustration of our galvanic cell, which is the electrochemical cell, where the electrons are going to be transferring and we're going to be getting that electrical energy, the labeling of the electrical energy that takes place at either the cathode or the anode as either oxidation or reduction is occurring is known as the half cell potential. Half cell meaning that we are only looking at, again, 1/2 of the cell, either the cathode or the anode. And we will talk about the overall cell potential in a second, but we're going to break down the 2 half cells first. And the reason why we're doing this is because we actually have on record a number of standard reduction potentials, which is by definition the potential of a reduction half cell. So all of these numbers that we have on record, all of these energies that we have on record, all correspond to half reactions. They're all half cells. Now the potential of a reduction half cell means that we've standardized all of the energies to the reduction form. And we will talk about what that means in a second, but we're going to be relying on our knowledge of the activity series to kind of make sense of it. So, looking at the rest of the definition, we are looking at the potential of a reduction half cell when the ion concentration is standardized to 1 molar and the pressure is standardized to 1 atmosphere. In addition, the measurement of the reduction half cell potential is all relative to a given standard electrode, and the standard electrode that we are working with and have been working with for like 50 or 60 years now is the standard hydrogen electrode. All right, so let's talk about how we get these measured standard potentials experimentally and why they're all from the perspective of reduction. So what is the standard hydrogen electrode? Well, we're going to put the emphasis on the word standard in the standard hydrogen electrode. So much like back in chapter 11 when we introduced standard conditions for the first time, I think it was for the first time, in reference to like standard temperature and pressure with PV equals nRT studies, or with energetic studies, we have discussed standard conditions there. Similarly, with electrochemistry, we have just introduced a standard concentration, a standard pressure, but we also have to have a standard electrode as well to make sure that the rest of our potentials that we have on record are all like relative to something. And the standardized electrode that we use is the standard hydrogen electrode. Sometimes this is shorthanded by the acronym SHE or SHE. So if you're reading in the text and suddenly you come across a SHE in all caps and you're like, who is SHE? SHE is the standard hydrogen electrode. All right, so the physical construction we can see in a diagram down to the right, which I will dissect in a second. But the standard hydrogen electrode consists of a platinum electrode, which platinum in the actual construction of the galvanic cell or the standard hydrogen electrode is simply a catalyst. So the platinum in the electrode is in contact with a 1 molar strong acid solution, so something that's like HCl or HBr. as well as it is in contact with H2 gas, and that H2 gas is at that standard 1 atmosphere. Similarly, the strong acid solution is in that standard 1 molar concentration. So we can see the physical illustration of the standard hydrogen electrode in a galvanic cell below, where it is the standard hydrogen electrode that is acting as the anode. So it is the H2 that is being oxidized, and as it is being oxidized through a catalytic reaction with the platinum that is, you can see present here, we're going to be generating some H plus in solution, as well as some electrons that are going to be coming up into the wire like so. And all depending on what we connect the standard hydrogen electrode to, so in this example, we're looking at it connecting to copper, which was the same cathode we just looked at in the previous example, we can see that there is a voltage present here of 0.342 volts. This is the standard reduction potential for copper. Right, since copper is the thing that is being reduced, it is on the reduction side. This value now becomes the standardized reduction value for copper. And the reason why we set this value as the standard to copper is we just assume, and by assume I mean we just declare that the energy of the standard hydrogen electrode, its voltage is 0. Physically, this does not make sense. Yes, the actual standard hydrogen electrode does have some value for its electric potential, but what we're doing here is we're just kind of resetting the baseline. So we're, whatever the value of the standard hydrogen electrode is, let's say it's, 0.5, we've just taken all of the other standardized reduction potentials and subtracted that value out. And fortunately, we are able to do this because voltages behave linearly. So we can add voltages to each other, we can subtract voltages to each other. If we scale up a voltage or if we scale up a reaction, we scale up the voltage, etc. Okay, so we have collected all of the standard reduction potentials for all materials in opposition to the standard hydrogen electrode, where if the standard hydrogen electrode is on the anode side, we can see the reaction that is listed here. If by chance the standard hydrogen electrode behaves more as the cathode, if it starts being reduced, if the H plus is turning into H2 gas and the substance in opposition is suddenly the anode, because that is what is spontaneous, we get this reaction that I've crossed out here. This is the reduction form, and we can see that the reaction is simply just written in reverse, and that is because of the reversible nature of these redox reactions. If you're being oxidized, you're giving off your electrons, and if you're being reduced, the exact opposite is happening and you are accepting your electrons. Okay, so here now we have an excerpt from table 18.1 in the textbook. This table is much larger than what I have illustrated here. I just have pulled out a chunk. This is the table of the recorded half-cell potentials that we are working with. And the standard hydrogen electrode, its chemical reaction we can see here, kind of highlighted in red. Now all of these reactions, reactions are written as reductions. Every single one of them. And again, that's for standardized reasons. That is convention. So if copper, which is the first element or material that we're looking at on this list, were to be set up in a galvanic cell with our standard hydrogen electrode, it would be reduced, and the cell voltage or the cell potential associated with that interaction would be the value that we just saw in the diagram, which is 0.34 if we round off to the hundreds place. And we can kind of see a measure then as we work our way down the table towards that standard hydrogen electrode, that all of the cell potentials, which are on the right, these are the cell potentials, all measured in volts, kind of decrease until we get to the standard hydrogen electrode where the value is 0. On the other side, as we continue working our way downwards, going and looking at lead and then tin and then nickel, The reason why these voltages become negative is because these materials are actually not easily reduced by the standard hydrogen electrode. When we are looking at these negative cell potentials down below, these are substances that become the anode. These are more easily oxidized. And so the entire table is organized based off of how easy it is for the material to be reduced versus how easy it is for the material to be oxidized, all standard to the standard hydrogen electrode, which is kind of in the center of the table. So materials that are higher on the table, as is labeled on the left-hand side, these are materials that are easier to reduce. And as we can see labeled on the right-hand side, the further down we end up on the table, the more easier that material is to be oxidized instead. And so if we want to put together a galvanic cell that is spontaneous, that the materials are going to then act according to their spontaneous desire for being either oxidized or reduced, we can use either the activity series, which we've learned before, or what we are learning now, the standard reduction potentials table. That should be an underline, not a scratch through. We can use the standard reduction potential table to predict the spontaneity of a given electrochemical reaction. For example, if solid tin were to be dropped into a solution of strong acid, we could ask ourselves, is the tin going to be spontaneously oxidized? So in order to figure out the answer to this question, we can go back to the segment of the half cell potential table, the reduction potential table that we have here. And our question is, does tin, which is here, does solid tin become oxidized when thrown into strong acid? And H+ is the representation of strong acid. Well, since tin is further down on the table than our strong acid, which is present in the standard hydrogen electrode, that means that tin is more easily oxidized. And if our question is, will the tin spontaneously oxidize? Our answer, therefore, is yes. The solid tin, which I'm going to go backwards again, this solid tin is more likely not going to be the product of reduction, but rather is going to cause an oxidation to occur. Right, so in other words, the further down we are on the table, the more likely the reverse reaction is going to be to occur. So our tin solid, write it out here, tin solid, when added into a solution of strong acid, yes, we would expect the tin to become oxidized. To come back up to the table, we can see that this first oxidation step results in tin with a 2+ charge. And so we would expect that the tin would then oxidize into its 2+ aqueous, its 2+ form, and we would also see some hydrogen gas as the product. All right, and we could go through the method to balance this chemical equation. In fact, we only need a 2 in front of this H+ in order to actually balance this reaction, meaning that we're going to have the transfer of 2 electrons from our tin into our H+, and this H+ is going to then be reduced, and it is the tin that will be oxidized. From this information, then, we can also suppose that our tin is going to be on the anode side of our galvanic cell, and it is the hydrogen that is going to be on the cathode side, since, again, oxidation always occurs at the anode, and reduction always occurs at the cathode. All right, so now that we've looked at the half cell potentials, we have a measure or a way to measure what the potential is at any one of these given half cells or any one of these given single half reactions in a redox reaction. We can now start putting chemicals together without necessarily having to look at the strong acid component. We can start taking, let's say, tin and copper and put them together and predict what the standard cell potential or the total electrical energy or energetic output is going to be for the cell. The standard cell potential in a galvanic cell, where again we're looking at some type of spontaneous reaction, the measure of the energetic cell or the cell potential is going to be positive. So positive cell potential values mean that we are working with a spontaneous galvanic cell. The standard cell potential, we can shorthand using this E naught of cell, like is illustrated down below. Now the E naught of cell, how we can calculate this without having to put these substances in contact with each other constantly, like how we can use the standard hydrogen electrode values to predict or calculate what the energy of our cell is going to be, is by taking the difference between the half cell potential for our cathode, right, and subtracting out the cell potential for our anode. So these are both going to be values that we can pull from the reduction potential table. We're going to be taking the difference in electrical potentials of the anode and the cathode. So that is what the standard cell potential is. We're looking at the potential energy difference. All right, so I'm going to do this here. Potential energy difference between cathode and anode. All right, so let's get an example of this. Let's actually look at a couple of values, right? We're going to look at a hypothetical situation and use our reduction potentials from the reduction potential table to calculate what a cell potential would be without ever having to step foot in a lab. So here we have such an example problem. Let's identify which half reaction is going to take place at the anode and the cathode. So we're not explicitly told which, but assuming that, again, the calculation of the energy of a galvanic cell meaning that there's going to be some type of spontaneous exchange, we would be able to predict that the E naught of cell is going to end up being positive. All right, so we can use the standard half reaction potentials to figure out which of the following reactions takes place at the anode and the cathode whilst simultaneously calculating this exact cell potential based on these values. All right, so the two reactions we are looking at, we have a solid silver bromide, which these are both in reduction form, So what that means is we're going to have to pick whichever one of these reactions that is going to end up taking place at the anode, whichever one is going to be oxidized. We will manually flip that reaction into the reverse, right? Again, according to the standard reduction table, all of these are written from the perspective of reduction. So the silver bromide in this first equation is being reduced by a single electron, turning into silver solid and bromide ion. The second species, the second compound, right, or the second reaction, the first compound in it, is magnesium oxide. Here it is combining with 4 hydrogen plus, so we see the explicit involvement of the water in this specific reduction reaction. We're also combining 2 electrons here, so I'm going to underline the 1 electron and the 2 electrons, creating some magnesium 2 plus in solution and generating some liquid water. All right, we have the reduction potentials for both of these half reactions as well. So in order for E naught of cell to be calculated, we have to take the standard energy of the cathode, and we are going to subtract the given energy of the anode. And we may not know what the cathode and the anode are in this case, but we can figure it out pretty quickly because there's only 2 ways that we can perform this calculation. If the first cell is the cathode, or if the second cell is the cathode. So like one of these has to be the cathode and one has to be the anode in other terms, or in other words. So the first hypothetical calculation, let's say that the first reaction is our reduction reaction. Let's say hypothetically the first reaction takes place, at the cathode. Let's say the second one takes place at the anode. Well, we're going to take both of these values and plug them into our equation just in a straightforward way. We're going to take 0.095 volts and we will subtract 1.230 volts. So what this gives us is a value of negative 1.14 volts, which is not positive. If our voltage is not positive, this is not spontaneous. which means that the first reaction, which we just arbitrarily, right, hypothetically labeled as the cathode, it can't be the cathode. And our second reaction, which we just arbitrarily said, well, let's try this at the anode, can't be at the anode. Because if we place the first reaction at the cathode and the second reaction at the anode, we get a negative cell potential. This is not spontaneous. So what this tells us is that we actually just in our first guess were exactly wrong. The first reaction is the one that has to take place at the anode, and the second reaction is the one that has to take place at the cathode. If we do this, right, and I'll just scratch out this hypothetical first trial, if we do it this way, we're going to now take the 1.230 volts and we are going to subtract out the 0.095 volts. And this gives us the exact opposite in terms of sign, a positive 1.14 volts. Because this value is positive, we now know that this is a spontaneous reaction, which means it can take place inside of a hypothetical galvanic cell, since galvanic cells contain spontaneous reactions, spontaneous redox reactions. What this also tells us is that the first reaction is the reaction that is going to be the oxidation reaction, since it is taking place at the anode, which means the spontaneous form of this reaction of the first one when mixed with the second is actually going to be the exact opposite. The products as they are listed are solid silver, and bromide ion are actually going to recombine, generating an electron, and then as a product, we are going to get some solid silver bromide. All right, you might be asking yourself then, well, we have 2 electrons in the second reaction that are necessary for this reduction to occur, and the first reaction, if it is the oxidation, only produces 1. So don't we have to scale this reaction up by 2? And if we do that, don't we also have to take this potential and multiply it by 2? I will answer both of these questions in turn. The first question, which is, don't we have to scale this first reaction up by 2? Yes, we do have to scale this reaction up by 2 if we want to generate 2 electrons. However, we are not working with absolute energies here. We are working with potential energies. And for that reason, we don't actually have to multiply this potential energy by 2 at all. We are not looking at the contents of the electrons as a part of this energetic calculation. We are simply looking at the difference between 2 potential states. And for that reason, we actually can, the calculation here for calculating the energy of the cell based on cathode versus anode is much simpler because the magnitude of the electrons in the transfer does not contribute to the potential energy of the cell. One sort of analogy that goes along with this is we can think of a waterfall, where the distance between the top of the waterfall and the bottom of the waterfall is a measure of potential energy. So we have this potential difference that is based on height only. If we're thinking actual physics, there's also a piece of like gravity in there. There are a couple of other terms, but the amount of water falling over the waterfall, which in this analogy represents our number of electrons, does not change the potential energy difference based on the height of the waterfall, right? It's the height only that matters, and that's giving you the calculation of your potential energy. Much the same thing is happening here. We can be throwing 1,000 electrons over this waterfall, but the potential energy difference between these 2 reduction potentials remains the exact same. And so for that reason, again, we do not need to multiply the potential of this half reaction by 2. We don't need to scale it up or scale it down at all because we're only looking at the potential difference between these 2 electrodes. All right, and that's it. Hey! Welcome to the end of your Friday lecture. Here we have a couple of example problems for standard reduction potentials. So if you want to get some more practice looking at either the standard hydrogen electrode, the half cells, the reduction potential table that we worked with, or even the calculation of E naught C, or E naught of cell, here we have a couple of problems that pertain to those concepts. I would also recommend you to look through the examples in the book. I mean, if you haven't been doing that for every chapter up until this point, I would absolutely recommend that you do this, since we are very quickly approaching the end of the semester, and getting some more examples more quickly is going to be more beneficial faster. So yeah, look through the book, read through those examples, see a couple more of examples pertaining to combining these redox reactions and how you can work with the calculated energy of the cell. All right, your last homework assignment of the semester. Homework for this lecture, which is Friday, is going to be due next Monday. Hey, and that is your last homework assignment for the entirety of Chemistry 202. So we are going to have one additional lecture next Monday lecture, where we are going to be revisiting reversible reactions with electrochemical cells, but I promise it is not going to be nearly as bad as any type of acid-base problem that we have been doing. We are actually just going to be looking at the more simplified, or having a more simplified discussion of reversible reactions in the electrochemical context, mainly focused around what is a battery and how can batteries be rechargeable, since the recharging of a battery is actually the reverse reaction of the battery being in the forward direction dispensing energy. I'm rambling now. I'll just see you guys on Monday. Class is dismissed.